Okay, so this is our final Maths 7016 lecture for Spring 2020. We're just going to do one example of approximating solutions of the heat equation. Now, as before, we'll just be doing like one or two iterations. To actually do it properly, you need to use VBA. Okay, so let's write down the heat equation. So the heat equation is K times second derivative of temperature with respect to distance is equal to the derivative of temperature with respect to time. Okay, and what we're going to do is we are going to approximate this using finite differences. Now, we may as well write down the finite difference things that we're going to be using. So we're going to use that the second derivative is approximately the next value minus twice the current value plus the previous divided by delta x squared. Delta x is the change in the variable. That's the second derivative, finite difference approximation, and then the first derivative is next minus current. It's kind of like rise over run divided by delta x. We're going to be using these. So these formulas will be given to you in this form and this form. Okay, so what are we going to do next? Well, we know what K is anyway. Oh, there's some other information here. So this is a rod, remember. So we've got a rod. It is insulated. It's thin. Yeah. It's 10 centimeters long. We'll probably use units of Now we're going to get into a bit of hassle here because the lambda that I'm looking at looks a little bit big. Let me just do a small calculation here. 0.835 by 0.1 divided by 0.02. No way. So the K I have is humongous, unfortunately. So I'm just going to change the question. I'm going to change this to 2 meters. And well, that changes the K as well. Oh crap. What I'm going to do is I'm not going to worry about the units. So don't worry about the units here. This will be meters. So it's a 10 meter rod now. Now you would say, what? I have to make this thing up here to be small. And if I'm not doing that, I'm not really doing this properly. Okay, so let's mesh the rod. So here's the rod now. It's got boundary temperatures. There's a 100 here and 50 over here. And actually 2 meters looks a bit big even. There, let's go for it. Okay, so we want to cut this up into lengths of 2 meters. So 2 meters, 4 meters, 6 meters, 8 meters, something like this. And we know the initial temperature, by the way, is 0. So that should probably be written as T of x 0. So when the time is equal to 0, the temperature at every single point is 100. That's the initial temperature. And we want to call this thing like T1, T2, T3, and T4. And this is the temperature at this point. Now, we haven't really included the time here yet, but that's okay. All right, so the schematic is saying we're imagining the time going up as such, and the schematic that we talk about is, we did this in the last lecture. So this is delta T, this is delta X, this is delta X, and now there's different ways of doing this now that I think about it. So I'll do 2 different ways. So this could be temperature. This is the standard way. Okay, let me just explain. So the TI, this is in the last video. So TIL means the temperature at XITL. And basically what we're doing is, okay, so say T2, X2 is 2 times delta X, something like that, and TL you're going in times of delta T. So the other way you could talk about this is that this is like a next in terms of T, in terms of time, and in any language this is the current. The temperature here is the next in terms of distance, and the temperature here is the previous in terms of distance. Okay. Right, so what we want to do is the heat equation, which I've kind of written up here, which is, we'll just write it down again, no harm, K times second derivative of temperature with respect to distance is equal to the derivative of temperature with respect to time. And what we want to do is derive an equation, and this I had to change the units around. Okay, so let's use the second derivative finite difference approximation for the second derivative. So this second derivative down here is approximately equal to the next in terms of x minus twice the current plus the previous over delta x squared. So we will get I think actually what happens here, just in terms of the units, is if I convert to meters, the K, and keep everything in meters, I think centimeters squares is a 0.01 squared, so that forces this to get small. So we'll just run with meters with these funny values, we won't worry too much about it. Okay, so what am I doing? So K, which is 0.835, don't worry about the units, and now this second derivative using this. So the next temperature to here in terms of distance is this one. Okay, minus twice the current. So what I'm doing here is I'm approximating, plus the previous, I'm approximating this equation. So I have an approximate equation that I will solve approximately over delta x. Now delta x here is 2, so this would be 2 squared. Okay, happy days. Equal to, now approximating this using this. So it should be next minus current over delta x. Now with respect to time, the next temperature is this one. Minus the current temperature is TIL. And then the change in x is actually a change in t is delta t. So maybe we'll just note at this time that the L's up here refer to time and the I's refer to distance. This is what you need to understand. This is written here as well. So the I's refer to distance, the L's refer to time. And then what you can do is you can, oh of course delta t is, we're saying is equal to 0.1. Is that you can solve this. Now actually this is something that people, like if you get to here, you really don't want to mess up the next thing, but if you carefully solve this, you find that the next temperature in terms of time at a point, if you solve this properly as per the last video, is equal to the previous temperature in terms of time at that point plus K delta T over delta X squared, and it's important that this is less than a quarter, and this is. Times this yoke here. So the next temperature in terms of distance, but the previous one, minus twice the current temperature plus the previous temperature in terms of distance. Now we'll find out what this lambda is in the calculator. Now obviously we don't want to introduce extra rounding error here if possible. Let's see what we get. Alright, I'm going to round this to, or don't, why round it? Lambda is equal to 0.020875. Yeah, I will round it just for the sake of this to make things easy for me. 0.021. Now that's obviously introducing rounding error, it's not good, but I've got a time and a space issue on the next page, especially because I've got 4 internal temperatures, which is more than I needed. Okay, so I have that the next temperature in terms of time at a point is the previous plus, we're going to take 0.021, and then the next temperature over minus twice the current plus the previous over in terms of x. And here's the dog. So let's see. If the dog goes mad now, I'll have to break this up into two. So let's go. So I'm going to do a number of them here. So I have initial temperatures. I'm going to have to pause here and go to the next video because the dog is on my lap.